You are welcome to my YouTube channel at GMAT41. In this video lesson, I would like us to look at an important law in electrostatics, Coulomb's law of electricity. Before we dive into this, I would like to firsthand say a quick thank you to all of you that have been tuning in to this wonderful channel. I so much appreciate. I want you to be assured of this very fact. And always be confident that there are a lot more you can get from GMAT41's YouTube channel. Alright, so let us get into this. In the study of electrostatics, when you deal with charges created without their being moved from one point to another, without transferring current, there is an important law that guides the force that exists between these charges. This law was propounded by Charles Augustin de Coulomb. Now consider that you have two charges. According to the law of charges, like charges will repel and unlike charges will attract. What is responsible for this repulsion and or the attraction in the case of like charges and unlike charges respectively? That is what I want us to quickly look at in this video. Like I stated, Charles Augustin de Coulomb was responsible for propounding this law. What does this law state? Coulomb's law of electricity states that the electrostatic force between two charges is directly proportional to the product of the magnitude of the charges and inversely proportional to the square of the distance between them. We are going to use F to represent the force, and we shall use R to represent the distance. You may still choose to use small d to represent the distance. The choice is yours. So according to Coulomb, the force will be directly proportional to the product, to the multiplication of these two charges, and inversely proportional to the square of the distance between them. Mathematically, Coulomb's law is written as F directly proportional to, let us use Q to represent the charges, so we're going to have Q1 times Q2. That same force is inversely proportional to the square of the distance between the charges Q1 and Q2. Now, if we use the knowledge of joint variation in mathematics, we can combine these two statements. This one for direct variation or direct proportion, and this one for inverse variation or inverse proportion. You can also call it indirect variation or proportion. So by joint variation, since this statement is defining force, this is also defining force. We shall pick one of the force, pick our sign of proportionality, and then combine these two statements, Q1, Q2, to 1 over square of the distance between the charges. And how do we combine these two statements? We shall multiply this first with this second. So we have Q1 times Q2, then times 1 over square of R. So you see clearly that F is proportional to Q1, Q2 divided by square of R. Now this is a statement, a proportionality statement. How can we handle this mathematically in terms of solving problem using this statement? We have to remove the proportionality sign and then introduce a constant. That constant will come with equal to, so we have F is equal to K. I'm using K to represent the constant. So once I introduce equal to K, equal to this constant of proportionality, it removes this sign of proportion. Are you following, right? This is going to be multiplied by Q1, Q2 over square of R, which will simply give us Q1, Q2 over square of what? R. We shall call this equation 1. So this is a mathematical equation describing Coulomb's law. Now, this K has been found experimentally to be equal to 1 over 4 pi times permittivity of free space. 1 over 4 pi epsilon naught. Okay, so I'm saying that K is equal to 1 over 4 pi epsilon. Now, there is something I want us to do here. Usually, we introduce subscript 0 down there in this epsilon to define what we call the permittivity of free space, the permittivity of vacuum. All right? Permittivity of free space. Epsilon naught. When I say E naught. Okay? Epsilon, Greek symbol. That being the case, we are going to substitute for this K using 1 over 4 pi E naught. Now, this 1 over 4 pi E naught has a value. I'm going to write it down here. It is equal to 9 times 10 to the power of 9. And the unit is Newton square meter per square Coulomb. Coulomb is the unit of charge. Is that okay? So when you get the unit of K, it's simply making K subject to the formula, which of course will be F square R divided by Q1, Q2. From there, fixing the unit of F, which is Newton, the unit of distance, which is meter, is going to be squared. Then per the unit of charge, which is Coulomb. C, that's what we use there. Remember, it is Q1, Q2. Two charges being multiplied, so the unit is going to be squared. Unit of charge, which is Coulomb, will be squared. This is the value of this constant of proportionality. Actually, this value is obtained by substituting for the permittivity of free space. I'm going to give it to you as notes. Is that okay? This permittivity of free space E naught is equal to 8.85 times 10 to the power of negative 12 farad per meter. Farad per meter. So actually, if you pick your calculator and then you press 1 over 4 pi multiplied by 8.85 times 10 to the power of minus 9, you would get this value. Is that okay? You would get this value approximately. So having said this, I guess we can now write that electrostatic force, according to Coulomb, is equal to 1 over 4 pi epsilon naught, that is permittivity of free space, Q1, Q2, all over square root of R. Shall call this equation 2. Equation 2 and equation 1 are the same. Is that okay? The only thing is I've decided to replace K with this quantity which it represents. Alright, if you choose to, you can just fix it 9 times 10 raised to the power 9 for this whole constant. At this point, we are done with Coulomb's law of electricity. This is an electrostatic force of either attraction or repulsion. Remember, if you're dealing with electric field, that force that exists there is either a force of attraction or a force of repulsion. Because according to the law of charges, like charges will do what? Repel. In that case, the force will be force of repulsion. For example, if you have positive charge and positive charge, or negative charge and negative charge. Then of course, unlike charges will attract. For example, if you have positive and negative charges, they will attract. So always remember, according to Coulomb's law, this force, electrostatic force, is either that of attraction or repulsion. At this point, dear friends, I'd like us to say something about this permittivity of free space, epsilon naught. Something very important. Because if we go by this equation 2 you are seeing here on the board, this is when the charges Q1 and Q2 are placed in vacuum. When they are placed in free space. Vacuum is a space relatively where there is no air. Even if there is air, the air is relatively negligible. Is that okay? So just assume as a no air condition, vacuum. So if you place these two charges in vacuum, in free space, the electrostatic force between the two charges is going to be 1 over 4 pi epsilon, that is permittivity of free space. I'm stressing that. Permittivity of what? Free space. In fact, let me indicate it. E naught is equal to permittivity of free space. Now, what about a situation whereby the charges are no longer placed in free space? Let us not assume that the charges, they are placed in a medium. That medium will have what we call dielectric constant value. Dielectric constant, we can also refer to it as relative permittivity. This dielectric constant actually helps to check the strength of that medium in order to know what the force is going to be like. This dielectric constant, also known as relative permittivity, a particular medium will have its value of that dielectric. So I want us to look at a situation whereby the charges are no longer placed in free space. They are no longer in vacuum. Okay? These charges are now placed in a medium, and you know the dielectric constant of the medium. It could be water. Now I must tell you that if you place two charges inside water, the force of attraction or repulsion between the charges will not be the same as the force of attraction or repulsion when these charges are placed in vacuum. So it becomes important for us to know how to obtain, how to determine the electrostatic force when charges are placed in a given medium which is no longer free space or vacuum. How do we apply Coulomb's law in this regard? Now watch as I carry out the analysis. First, we are going to define what we refer to as the dielectric constant, also known as relative permittivity. Permit me, please, to use K subscript R for it. One can decide to use capital D, the choice is yours, as long as you define what it represents. So let K subscript R be equal to relative permittivity, okay, or dielectric constant. Now, what is the mathematical formula for dielectric constant? Kr is giving us the permittivity of any medium divided by the permittivity of free space. So what dielectric constant of a medium will do is simply to relate the value of the permittivity of that medium to the permittivity of a vacuum, epsilon naught. So the formula is, permit me to use subscript R here as denominator. Okay, what I try to achieve here with all these symbols I'm using is this. Dielectric constant of a given medium equal to the permittivity of that medium. Permittivity of that medium, then divided by the permittivity of free space or vacuum. Now, if you look at this, you would agree with me that to get the permittivity of any medium, that would mean that we have to cross multiply. So that permittivity of any medium, alright, is not going to be the permittivity of free space multiplied by the dielectric constant of that medium. Take a look at that. At this point, we are going to do something which is very significant when dealing with Coulomb's law. Okay, something that most times we don't give attention to it, but exists and is very important because that is what would help us to quickly determine the electrostatic force between two charges when they are placed in any medium. What we are going to do is this. I want to say something very important now. It is true that usually we write Coulomb's law in terms of permittivity of free space. But the truth of the matter remains that with this permittivity of free space, we have modeled, we have restricted Coulomb's law to vacuum. Introducing this permittivity of free space, we have restricted Coulomb's law to a condition where we now assume that the charges are placed in what? In vacuum, in free space. Of course, that is why we got this value 9 times 10 raised to the power 9. So, suppose you want to apply Coulomb's law to a case where the charges are now placed in another medium which is no longer vacuum. You can't use this permittivity of free space here directly. Oh, 1 over 4 pi E naught. No. In that case, 9 times 10 raised to the power 9 would no longer be the value of this constant. It's going to be reduced by a certain quantity, which is the dielectric constant in that case. See, in that case, what is going to happen to equation 2 will now be, from equation 2, F is equal to 1 over 4 pi, then multiplied by permittivity of any medium. Permittivity of what? Any medium. So you can say that epsilon sub r, permittivity of any medium. Then multiply by q1, q2 divided by what? Square root of the distance between them. I feel like this should be the general expression when dealing with Coulomb's law. Now with this equation, we are no longer restricting Coulomb's law to free space only. We are now saying that, okay, the charges can be placed in any medium with a given permittivity. Alright? And so whatever that medium is, all we now have to do is to get the permittivity of that medium. But then, to get the permittivity, you need this relationship. That permittivity of any given medium is equal to permittivity of free space, permittivity of vacuum multiplied by the dielectric constant, by the relative permittivity of that medium. Therefore, this implies that our F, the electrostatic force, would now be equal to 1 over 4 pi. Then, in place of this permittivity of the medium, we are going to substitute permittivity of free space multiplied by the dielectric constant of that medium. So we have 1 over 4 pi. Then in place of this, we're going to have this times dielectric constant. I hope I'm making sense, right? So we're going to multiply it by q1, q2, and then divide by square root of r. Okay, having done that, I'd like you to watch this, please. 1 over 4 pi, permittivity of free space. Look at that. This force with 1 over 4 pi, permittivity of free space, multiplied by q1, q2 over square of r. Let me dot this as well too. Take note that this kr is not among what I dotted there, because I want to show you something. 1 over 4 pi E naught q1, q2 divided by r squared is equal to the electrostatic force in vacuum. In what? Vacuum. So permit me to use FV for it. Permit me to use what? FV. That is the electrostatic force in vacuum. That simply means that this formula, look at that, equation 2, Coulomb's law, is actually electrostatic force between charges in what? Vacuum. I can use F subscript V for it. I think at this point, let me go back now and do that. Let me put F sub V, which is the electrostatic force in what? Vacuum. And now I'm trying to look at the situation where the charges are now placed in a given medium. So having said this, this formula you're seeing actually defines the electrostatic force between two charges when they are placed in what? Vacuum. Now watch. What would now be the force when they are placed in any other medium? That would imply that this force, F, would now be equal to, watch, in place of 1 over 4 pi E naught, Q1, Q2 over R squared. That defines the force in vacuum. So I'm going to write FV. Force in what? Vacuum. Which makes use of this formula which we generally are used to. You observe that there is K sub R in the denominator. That is the dielectric constant of that medium. So this is going to be divided by what? K sub R. We have established the fact that the force in any other medium is equal to the force in vacuum divided by the dielectric constant of that medium. We can put this down grammatically. The electrostatic force between two charges in any medium equals the electrostatic force between the charges when they are placed in vacuum, which of course makes use of this formula 1 over 4 pi A naught Q1, Q2 all over R squared. So it's equal to that force when they are placed in what? Vacuum. divided by the dielectric constant of that medium. And that gives us this equation. So I'm going to call this equation alpha, and I'd like to refer to this equation as a general equation in terms of stating Coulomb's law. Alright? So that it takes care of any other medium. The same as this. Look at it. This formula and this formula, they're the same. But this will help us to solve certain kind of questions like what I am going to dictate now. We are going to quickly get the result. Are you ready? So we go. Two charges are placed in vacuum and the electrostatic force between them is 40 Newton. Find the electrostatic force between these charges when they are placed in a medium of dielectric constant 80. What is the answer? F, the force between the charges in the medium, will be equal to the force between the charges in vacuum divided by the dielectric constant, which of course is going to give us that the force in the medium is equal to 40 divided by what? 80. 40 over 80 will give you 1 over 2, which is the same as 0.5. Just imagine the force when the charges are placed in that medium of dielectric constant 80 is equal to 0.5 Newton. Whereas when the charges are placed in air, the force was 40 Newton. Does that send any information to you? When you place charges in vacuum, alright, you expect greater electrostatic force between these charges. When these charges are now placed in any given medium, the force between the charges is expected to what? Reduce. Sometimes you can find the fractional decrease. Like this question that I dictated a moment ago. Force in vacuum, 40. Dielectric constant of another medium, 80. What is going to be the force in that medium? If the force in vacuum is 40, whatever value it is, are you following, right? And then you are now placing the charge, the two charges in a given medium of dielectric constant 80, then the force in that medium would be the force in vacuum reduced. How many times? 80 times. Alright? Reduced by 80 times. So can we just quickly try this out? Alright? The force between two charges in vacuum is given as 20 Newton. By what value will the force be reduced if the charges are placed in a medium of dielectric constant 7? The result is simple. The force between the charges when they are placed in the medium of dielectric constant 7 will be the force in vacuum reduced 7 times. So that means that the force in the medium is going to be 1/7 the force in vacuum. So whatever the force in vacuum is, all you have to do is to divide it by what? 7 in that case. I hope you enjoyed this video lesson explaining critical aspects of the application of Coulomb's law of electricity. Please like and subscribe to my YouTube channel. Share this video lesson so that other scholars will benefit from it. Remember, your examiner reserves the right to ask you a question in any direction that he or she wants or likes, And so it is important for you to be well grounded on the use of Coulomb's law of electricity. If a question is given to you and the value of the charge is Q1, Q2 are given, the distance between them is given, and there is no statement as to whether the charges are placed in any medium, nothing. You were not told that these two charges were placed in any medium, then use the formula, which is this, 1 all over 4 pi E naught, permittivity of free space, Q1, Q2 all over what? R squared. However, if you are told that the charges are placed in a given medium of dielectric constant, the value of the dielectric constant is given to you. Please, the formula you're expected to use will be this, because you need to account for the reduction in force when these charges are placed in that medium. A fast way of dealing with such question when they are placed in a given medium, is using this formula to calculate the supposed or expected force or the expected electrostatic force between the charges when they are placed in what? In vacuum. Then divided by the dielectric constant of the medium given to you. Alright, I've shown you how you apply this equation alpha, very important. Please, I'd like to give you an assignment, okay? You can solve this question I'm about to dictate and then leave your answer in the comment section. Let us see how far you were able to analyze that problem. So we go. Two charges, 5 Coulomb and 10 Coulomb, are separated by a distance of 5 meters. A. Calculate the electrostatic force between the charges. B. If the charges are placed in a medium of dielectric constant 4, what would be the electrostatic force between the charges? So friends, solve this question and drop your answer in the comment section for review. Let me see what your answers to this question are. If you have any question on your own, you can leave it in the comment section, and of course I'll be right there to respond. Please remember to share this video lesson so that other friends, scholars like you will benefit from it. Like and subscribe to my YouTube channel, and please I'll appreciate you to recommend it to your friends. I look forward to seeing you in my next video lesson, where I'll be treating the electric field intensity, also known as electric field strength, that exists in an electric field. Alright guys, so till then, have fun with your studies.